The James Webb Space Telescope, JWST, has become one of the most significant instruments in modern astronomy, offering new insights into the vast and mysterious universe we live in. With its unparalleled sensitivity and advanced imaging capabilities, JWST has already revealed incredible discoveries that challenge our understanding of the cosmos. Most notably, it has observed galaxies that are far too massive and developed for their early stages in the universe's history. This discovery raises some unsettling questions for cosmologists and astrophysicists, as it calls into question key aspects of the current model of the universe's birth and early evolution. For decades, the Big Bang theory has been the bedrock of cosmological science, describing the universe as originating from an incredibly dense and hot singularity roughly 13.8 billion years ago. According to this theory, space-time itself began expanding rapidly from this point, and over billions of years, galaxies, stars, and planets formed from the remnants of the initial explosion. It's a theory that has stood the test of time, with robust evidence supporting it, including the cosmic microwave background radiation, CMB, the faint echo of the Big Bang that fills the universe. Yet, despite the strength of the evidence, recent observations have led some scientists to re-examine this explanation for the universe's origins, suggesting that the truth might be far more complicated. With the data coming in from the James Webb Telescope, astronomers have been forced to confront the possibility that the universe could be much older, more complex, and more dynamic than previously imagined. The fact that some of the galaxies JWST has observed appear to be far larger and more evolved than they should be at such an early stage in the universe's history is deeply puzzling. These findings suggest that our understanding of how galaxies form and evolve might need to be overhauled. But they also raise even deeper questions. Could it be that the Big Bang was not the true beginning of the universe, but just one event in a series of cosmic transformations? What if the universe we know is not a one-time event, but part of an endless cycle of birth, death, and rebirth? At first glance, this idea might sound like something out of a science fiction story. But in fact, this very concept has been considered by scientists, philosophers, and ancient cultures for centuries. The idea of a cyclical universe, one that undergoes continuous cycles of expansion and contraction, isn't new. In ancient India, for example, the Vedic texts describe the universe as undergoing repeated cycles of creation and destruction. The Maya civilization held a similar view, seeing time and existence as cyclical rather than linear. These ancient ideas may have more in common with modern scientific theories than we once realized. For years, cosmologists have worked under the assumption that the Big Bang marked the definitive start of everything, the moment when the universe came into being from a singularity. This view is supported by numerous observations, including the expansion of the universe, the presence of the cosmic microwave background radiation, and the abundance of light elements like hydrogen and helium, which match predictions made by the Big Bang model. However, as scientists like Stephen Hawking and others have pointed out, the question of what happened before the Big Bang may not even make sense. According to Hawking, time itself may have begun with the Big Bang, and asking about what happened before it is like asking what lies north of the North Pole. It's a question that simply has no meaning. This view posits that the Big Bang didn't have a cause in the traditional sense. Instead, the universe just emerged, governed by the laws of physics, and that's all there is to it. But this explanation is far from satisfying for all scientists. Many are not content to accept that the universe could have come from nothing, or that there was no cause for the Big Bang. These unanswered questions have led to the rise of alternative theories, ones that suggest that the Big Bang may not have been the beginning of everything after all. Instead, it might have been just one stage in a much larger, ongoing cosmic cycle. One of the most intriguing of these ideas is the concept of the Big Bounce. In this model, the universe undergoes an eternal cycle of expansion and contraction. After the Big Bang, the universe expands and evolves, but eventually, the expansion slows down, halts, and reverses, leading to a big crunch, where all the matter and energy in the universe collapse back into a singularity. Then, after reaching a critical point, the universe rebounds, and another expansion begins, this time, perhaps creating a new Big Bang. If this process repeats infinitely, the universe would experience an endless series of cosmic cycles, each starting from a big bounce rather than a big bang. The idea of a cyclical universe is not just a whimsical notion, it has been taken seriously by many leading cosmologists. For instance, the physicist Roger Penrose has proposed a model known as conformal cyclic cosmology, which suggests that the universe goes through cycles of eons, each one starting with a big bang and ending with a big crunch. According to Penrose, the key to understanding this cyclical nature of the cosmos lies in the concept of entropy. As the universe expands, entropy, a measure of disorder, increases. When the universe contracts again in a big crunch, this entropy would be wiped away, allowing for a fresh new beginning. This process would allow the universe to start anew, without the need for an initial cause or an infinite amount of time. But while this theory is fascinating, it is not without its challenges. One of the most significant problems with the cyclic model is the issue of entropy. According to the second law of thermodynamics, entropy always increases over time in a closed system. This means that the universe should become more disordered with each cycle, leading to a state where everything is spread out and incapable of forming stars, planets, or galaxies. Over time, the universe would essentially reach a state of maximum entropy, a so-called heat death, in which all matter is evenly distributed, and no more work can be done. If the universe truly undergoes an infinite series of cycles, then this process would have to account for the ever-increasing entropy from cycle to cycle. Some proponents of the cyclic model suggest that the universe could reset itself at the beginning of each new cycle, with the laws of physics somehow allowing for a fresh start, free from the accumulated entropy of the previous cycle. But this raises new questions. How could this reset happen? And why does the universe seem to follow the second law of thermodynamics in the first place? One possible solution to the entropy problem comes from the field of quantum gravity. Quantum gravity is an area of theoretical physics that seeks to reconcile the theories of general relativity and quantum mechanics. According to some quantum gravity models, spacetime is not continuous, but rather made up of discrete units, like tiny loops or quantum circles. These loops would form the fundamental structure of spacetime, and they could potentially provide a way for the universe to reset itself at the start of each new cycle. The idea is that as the universe contracts in a big crunch, the fabric of spacetime itself could undergo a quantum transformation, eliminating the accumulated entropy and allowing for a new expansion. One such model is loop quantum gravity, which suggests that spacetime is fundamentally granular at the smallest scales. This idea has profound implications for our understanding of the universe's origin. In the loop quantum gravity framework, the singularity that was thought to exist at the beginning of the Big Bang would not actually exist. Instead, the universe would experience a bounce, a transition from contraction to expansion, driven by the quantum properties of spacetime. This theory challenges the traditional view of the Big Bang and suggests that the universe could have undergone a big bounce, where each new universe is born out of the collapse of a previous one. In this scenario, the universe could be part of an eternal cycle of creation and destruction, where each cycle starts with a big bounce rather than a singularity. This model allows for the possibility of multiple universes, each emerging from the collapse of a previous one. But this idea raises a number of complex questions. For instance, how would the quantum properties of spacetime prevent the universe from simply collapsing into a singularity again? And what happens to the information about the previous cycle? How is it erased or transformed in a way that allows for a fresh start? Interestingly, the concept of a cyclic universe also helps to explain some of the larger mysteries of cosmology. For example, the uniformity of the universe, the fact that distant regions of space appear to be nearly identical, despite being separated by vast distances, is a long-standing puzzle. In the Big Bang model, this uniformity is explained by the theory of cosmic inflation, which posits that the universe underwent a rapid, exponential expansion in the moments after the Big Bang. This expansion smoothed out any irregularities in the distribution of matter and energy, leading to the uniform cosmos we observe today. However, the idea of a cyclic universe offers an alternative explanation. If the universe undergoes a series of cycles, with each cycle resetting the distribution of matter and energy, then the uniformity could be a natural result of this ongoing process of cosmic rebirth. Despite these compelling arguments, the idea of a cyclic universe is still a topic of active research and debate. The evidence for and against the cyclic model is far from conclusive, and there are still many unanswered questions. For instance, the question of what happens at the end of each cycle remains a mystery. Does the universe ultimately collapse into a singularity, or does it experience some other kind of transformation? And if the universe does bounce back after each cycle, how do the fundamental constants of nature, such as the speed of light and the gravitational constant, remain the same from cycle to cycle? While these questions remain unanswered, the idea of a cyclic universe offers an exciting new perspective on the nature of time, space, and existence. It challenges the conventional understanding of the Big Bang as the definitive beginning of the universe and opens up new avenues for exploration. The discoveries made by the James Webb Space Telescope are providing us with a glimpse into the unknown, a window into the distant past that could reveal answers to some of the deepest questions about our universe. Whether or not the universe is part of an eternal cycle, we are only beginning to scratch the surface of what could be one of the most profound and exciting revelations in modern science.